Welcome to lesson 46, not 406, 46. Cross off that zero, please. True power versus apparent power in a series RLC circuit. Yep, we're going to have to learn a concept today, and it's called apparent power. So in order to get at what is this thing called apparent power, what makes it different from true power, I want to consider three things. I want to consider DC circuits first, an AC circuit that has only a resistor, so that would be this one, and then our favorite, the AC circuit, which means you're applying AC electricity to it, which has a resistor, an inductor, and a capacitor, an RLC circuit. I'll get that stuff out of the way. So the DC formulas, wow, we kind of started the class with these kinds of things, right? So you remember this good old Ohm's law formula. E equals I times R, where E, maybe I'll put this for reference. You probably have this figured out by now, but let's just say that's volts. This is current, which is in amps, and R is in ohms, right? Okay, so that's your standard Ohm's law, E equals IR. And then we had something that we called Watt's law, another formula, which was power is equal to voltage times current. Volts times amps gives you power, and the power is in units of watts, hence the name Watt's law. So those were our two fundamental formulas. And you might remember we had a whole power wheel, right? We had 12 formulas that you can get basically by rearranging these two formulas, plugging one formula into the other, rearranging some more, and so on. Of those 12 formulas, my three favorite are the two that you're looking at plus this one. This is another version of a power formula. Let's say you don't know the voltage, but you know the current and the resistor. Well, you can use that formula instead. So these are probably the top three DC formulas, right? And P, of course, is in watts again, and so on. Okay, so those are all familiar. Now, what happens if instead of using a DC current, you use an AC current? Well, I'm going to use an AC current that only has a resistor. If you do that, the formula is completely different. You ready? So Ohm's law, instead of looking like that, it looks like that. Do you see the difference? There is a difference, actually. The difference is that there's no such thing as just a steady voltage. There's an RMS voltage, root mean square voltage, and then the current, you would use the root mean square current because IRM, no, that's not it. RMS is what I'm trying to write here. The current, you use the RMS value of current as well. So remember, the waves are going something like this, and then the RMS current would be about this, right? So here's 0, here's this, right? So this is called your peak current, and your RMS current happens just about halfway to the peak, right there. 0.707 times the peak. Remember this stuff? The RMS is 0.707 times the I peak. So what's different about these formulas is that you have to stick in the RMS values. Now, that said, it usually gets to be pretty cumbersome to keep writing RMS. So usually we just write it the same, but we kind of understand in the back of our heads, hey, this is AC, I'm supposed to use RMS values. And that's exactly what, oops, I need a pencil for this one. You know what? I need a thingy for this one. That's what I need, a thingy. For AC formulas, use ERMS and IRMS in place of E and I, okay? Big deal. So like I say, the formula is kind of different. It looks exactly the same, but it's kind of different because we're just getting lazy and not writing RMS as our subscripts. If you believe me on that one, then maybe you'll believe me on this one too. So there's the very different power formula. Okay, so again, what's really different, if you compare this one to this one, what's really different is that the E is an RMS and the I is an RMS, a root mean square value. The power is still watts. That's the same. It's not like RMS watts or anything. It's just watts. So the power is still watts, and everything's good in that sense. And then this formula here also looks awfully similar. There is a difference. You're using an RMS current, but other than that, it really is the same formula. So again, Use ERMS and IRMS. That's really the only difference there. Now so things aren't so bad if all you have is a resistor. But you go bringing in a coil and a capacitor on top of it all. Okay, now we really have to monkey with the formulas a little bit. First of all, what have you been doing for homework? These past few things we've been like adding up phasors and stuff, right, to get the impedance. So impedance is what you call the total resistance, so to speak. I shouldn't say total resistance, but it's the total ohms. Remember, if you wanted to get the total ohms, let's say this was, I don't know, 3 ohms, 2 ohms, and 5 ohms or whatever. If these were all purely resistors, you would just add up. 3 plus 2 is 5, 5 plus 5 is 10, and you say 10 ohms. But for an AC circuit, you can't just add up because you have to add vectors. One vector goes this way, one vector goes this way, one vector goes this way. You end up adding them up and you get what's called the impedance vector, and the length of that vector is kind of like your total ohms. So you have to use the impedance in place of resistance. So that does look different, doesn't it? Cool. Now this is still going to be RMS and RMS. That's not different. Okay, so whenever you have AC, you're talking about RMS values of E and I. But the Ohm's law, instead of having an R, it has a Z in it for the total impedance. Remember, Z kind of means R, but you can't call it an R. And why can't you call it an R anyway? Do you remember we were talking about this has a certain resistance, but this has a certain reactance, and this had a certain reactance. It's all ohms. But why, do you remember, we actually mentioned this, why do we call these reactances instead of resistances? And the answer is because only the resistor gets hot. Come on, you. Only the resistor gets hot. The resistor, because it's hot, it's basically leaking energy to the room or whatever, to the environment. It's hot, it leaks energy to the environment. These do not get hot. So I'm going to put not. They do not get hot. They do not leak energy to the environment. They don't. There's no loss there. This is the dissipation over here. Dissipation is in the resistor only. Okay, that is a key physical point for this lesson. The actual the resistor only is where you actually lose some of your circuit energy out to the environment in the form of heat. Okay, so the coil and the capacitor theoretically are perfect. They're like perfect springy. I don't know how to explain it exactly, but yes, there's a pushback, but the pushback is a magnetic pushback. It's not like in the resistor where it's actually like a friction pushback. Friction makes things hot. Friction you lose, but these are like springy. They just push back, but without any loss. So anyway, you got to use the Z. That's the big thing there. Now, for the power, let's go back to blue here. You also have to use the Z, except how are you going to use the Z? Well, you're going to write it this way. You're going to write P equals EI, and the Z is kind of hidden in there because, the voltage that you get depends on the current, but it also depends on the resistance, or should I say the impedance. And so the thing is, this E and this I, since they're both the RMS values, they're both taking into account not just the resistor, but they're taking into account coil and capacitor, the pushback of the coil and the capacitor. So it's like this is too high then. So what we call this is apparent power, because it's not truly dissipated, not all of it. Some of it is. Some of it is being dissipated in the resistor, but not all of it. The pushback from the coil and the capacitor is not dissipating any energy. It's not heating up. It's not getting hot. You're not wasting anything there. Now, because it's apparent power, we don't want to call it watts anymore. So watts are true power dissipated. I'm kind of being redundant. Power dissipated, true power, it kind of means the same thing. These, we have to call them something else. So what are you going to call it when you multiply so many volts times so many amps? Well, if you don't want to call it a watt, you can call it a volt amp. And that's what they call them, volt amps. Apparent power is called volt amps. And again, it's going to be a bigger number. This is always going to be a bigger number than the true power. As far as this formula goes, hey you, go down. Okay, so as far as this I squared R, well, we're going to use I squared Z again. And again, because the Z is determined by taking into account not just the resistor, but also the coil and also the capacitor, then it's going to be a bigger number than the resistor. And so this number is going to be too high, and so we call it an apparent power. And again, this is in volt amps. Okay, so look at these notes down here now, maybe in a different color. Note number 2, the true power is in watts, and it refers to the resistor only, meaning the power is only dissipated in the resistor. So again, in this middle column, I was talking about a circuit that only had a resistor. So this was watts, because everything was in a resistor, right? So that was fine. But apparent power, and now I'm on the next line, line 3, if you please. Apparent power, which is called volt amps, includes the effects of L and C. Again, they do push back. You do have to fight against it. There's a sort of a power involved there, but it's not dissipative. It doesn't heat up and waste energy to the surroundings. So if you're taking into account the pushback of the coil and the capacitor, in other words, you're using a Z instead of an R, then the power that you get is going to be an apparent power in volt amps. And it's the same here because the E adjusts itself according to the Z, not according to the R, but according to the Z. And so this is also in volt amps, okay? So that's our big thing we got to get used to today. So let me try to clean this up a little bit here. Ooh. Actually, I kind of like maybe I like the green on the P apparent. That looks good. Okay. So, oops, come on, you. And then the other thing we're going to do is we're going to fix my equals. Okay. Now, there's something called power factor, but let's see, do I want to do that now? I don't want to do that yet. I'll come back to power factor. Let's go to page 2 and start looking at this example here. So example 1, we have an RMS current of 14 amps. Okay, so that's your IRMS. 14 amps. It's applied to a series RLC circuit. Okay, so we have a series RLC circuit. R is 100 ohms, that's this one. The coil X sub L has 40 ohms. Again, that's a reactance, not a resistance. 40 ohms, and the capacitor has 60 ohms. Find the following. Find the impedance and phase angle. Well, that's an old homework. We've done that before, but let's remember how it goes. So remember, you draw the resistor to the right. The resistor is 100 ohms straight to the right, which means it has an X component of 100 and a Y component of 0. The coil goes up, and I remember that because L kind of stands up, right? So the coil is pointing up. It's a vector pointing up, and it's only 40, so try not to make that as long. So your coil reactance is 40 ohms. It has an X component of 0, but a Y component of 40. It's straight up. And then your, your capacitor, 60 ohms, so this vector is going to be a little bit longer. It's not quite to scale, but you kind of get the idea. And this has it's all Y component. There's no X component. It's straight down. Down means negative Y direction, 60 ohms. Okay, cool. So those are our 3 phasors that represent the resistor, the capacitor, the coil. And then what you got to do is you got to get your Z by adding these up, and I usually use a red for Z. So notice that if you add this up, let's kind of get this out of the way. If you add up your X and Y components separately, in the X direction we have 0, 0, and 100. And in the Y direction we have 40, take away 60 is a negative 20. Plus 0 is still a negative 20. And so our impedance phasor has an x component of 100, which means the same as the resistor, and has a y component of negative 20, which will be somewhere around, here-ish. So here's our impedance vector, and we can maybe write the coordinates here. And that we can use to get our ohms. Remember, you would find basically the length of that vector, take the 100 squared, and we're going to square it anyway, so I don't bother to put the negative in, because as soon as you square it, it's going to go positive. So we get the 100 squared plus the 20 squared, add them up, square root. Let's see what I got here. 100 squared plus 20 squared equals, square root of the answer equals SD button. Whoa, not that button, SD button. Whoa, I lost it. Okay, 100 squared, 100 squared plus 20 squared equals square root of the answer equals SD equals, okay, there we are. 101 point, let's see, how many decimals do I want to play with here? 101 point, I guess I'm going to carry a bunch. I'm going to go with 6 sig figs, 980. We don't usually need 6 sig figs, but you'll see why I'm doing this in a little bit. So that's the impedance in ohms, 101.98 ohms. And remember the phase angle was this. Notice the voltage is going to, the circuit voltage is going to lag the circuit current. Why? Because the angle's negative, and that means lag. So to get that angle, you would do the old shift tangent of y over x. So y is negative 20 over x is 100. So shift tangent of basically negative 0.2 gives me a phase angle of negative 11 point, and I'm going to carry some decimals on this too. Looks like 3099. I guess we could call that 3. Well, if I want 6 sig figs, I'll take 6 sig figs. 11.3099 degrees. Again, we don't usually use 6 sig figs, but I am this time. And you'll see why. Okay, cool. We got the impedance and the phase angle. Cool. Now, find the voltage across the circuit. Now, what you could do is you could go back and refer to our table. We need the voltage across the circuit. I'm thinking we need it in blue, actually. We need the voltage across the circuit. So coming back up to page 1 in that table, we've got one of these kinds of circuits, an RLC circuit. We want the voltage. Well, here's one way to get the voltage. E equals I times Z. So I come back down to here and I say, yeah, it's my formula. E equals I times Z. So all I got to do is take my I, which they gave us, right? Yeah, they told us the IRMS was 14. So it's 14 amps times the impedance that we just solved for, which is 101.980 ohms. Let's multiply those two things together. We're going to have us a voltage. 14 times 101.980 equals. So with a lot of sig figs, 1427.72 volts, which we should really write as 1.42772 kilovolts. That would be the better answer. But for our purposes here, it's like 14,000 volts. Is that right? 1.4. Okay, good. That's what I got before. I'm just making sure. Okay, the apparent power. Apparent power. I'm going to put the APP on there to emphasize we're talking about the apparent power here. So if you want the apparent power, coming back up to this table to look for a formula, looks like we've got two choices. You could use I squared Z, or you could use E times I. Doesn't matter. I suppose you can do both, but well, why not? So I could go take the E times the I, or I could take the I squared times the Z. Let's just make sure they come out the same, because I like to do that now and then. So the E is, if I use regular volts, is 1427.72. And the amps, remember the amps was 14. These are RMS values now. And if I take the 1427.72 and I multiply it by the 14, I'm getting 19,988.08. Apparent power. Do not say watts, say voltamps, okay? Or really 19.98. Erase you. 19.988 kilovoltamps. I've seen kilovoltamps before too. If you did it this way instead, if you use this formula instead, if you took the I and squared it and then multiplied it by the Z, what was our Z again? 101.908.980. Let's hope this comes out exactly the same. 14 squared equals times 101.98. This time I'm getting 19,988.08. Ha! How about that? That's the groovy part about carrying all these sig figs. Everything matches perfectly. So again, that's apparent power. That's voltamps. Maybe I'll make that check mark look like a V now. Voltamps. 19,988.08 voltamps of apparent power. What is the actual power that's being dissipated? This is important because this is like loss. This is like you actually lose this. Your circuit is sucking this away from you. The true power dissipated. Well, there's two ways that you can calculate this. And that's why I sort of, well, two ways. One way is to go like this. Keep in mind, true power, or maybe I should say power is truly. How does that sound? Power is truly dissipated in resistor only. Okay? Only lost. You only lose power. You only dissipate power in the resistor. Only the resistor. So if you want the true power, what you would do is you would ignore the coil and the capacitor. In other words, you'd use R instead of Z. It's the same current all the way through the circuit. So I could use I squared R. I is 14. And then remember, the R was exactly 100 ohms. None of this 101.98, that's the impedance. The actual resistance was 100. So 14 squared equals times 100. You end up with 19,600. And these are actually watts. Or I really should say 19.6 kilowatts. But notice the difference between this number and this number. 19,988 versus 19,600. Apparent power is always going to be bigger than or equal to the true power. Okay? Because again, the apparent power is taking into account more pushback. It's taking into account pushback from a capacitor and a coil, so it's going to be bigger. So it's going to look bigger. So, but this is the actual watts down here, the true power. So true power, apparent power, two very different things. Now I want to show you what's the other way. The other way, what you do is you take P true, this is another formula I'm going to give you, is P apparent times what's called the power factor. PF means power factor. Factor is something that you multiply. So a power factor means you're going to multiply the power factor times the apparent power to get the true power. And what is the power factor? Well, for now, I'll just tell you. It's the cosine of the phase angle. How about that? Who'd have thunk it? Cosine of, and what was our phase angle? We solved that in part A. Phase angle was negative 11.3099 degrees, right? Negative 11.3099 degrees. And so if you, well, I guess I can just type that out right now. Cosine of negative 11.3099 degrees is, and I'm getting a power factor of like 0.980587, and it will you, and it keeps going like that. But if I just, while it's sitting there on my calculator right now, I'll just say times. I'll put the apparent power in 19,988.08 times the cosine of the negative 11, blah 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 blah. What I'm getting here 988.08 is, I am getting 19,599.9. I think at this point we're going to round it up because then it's a perfect match. So these are our watts. So you've got two choices on how to find the true power dissipated in a series circuit like this. One way is to take I squared times the R, using just the R, not the Z, but the R, because it's the R is where the dissipation is. Or, this is a formula you need to know because it's going to happen all over the place. You can get the true power by taking the apparent power times the power factor. What's the power factor? The power factor is the cosine of the phase angle. Ain't that something? Just cosine of the phase angle. Works like a charm. So what I want to do now is I want to go back up to page 1 and finish where it said power factor. Now let's try to present this a little more formally here. How do you get a power factor? You get a power factor. Let's get it in a purplish color. Come on, you purplish color. Okay. So remember that we get our Z. Well, I guess I'll do this. We get our Z by adding vectors together, right? So the Z is up here. This was the resistor, and then this is XL minus X sub C. So we might have had some, we might have had a certain L and a certain C, and let's just pretend we already subtracted that. And so it's all going up like this. Okay. Here's the thing. Z is big. In our case, it was the 101 point. What was it again? 101.980. There we go. And the resistor was 100, right? If you want the, apparent power is based on the Z, the true power is based on the R. So if you want to turn your Z into an R, this same ratio would turn your apparent power into a true power. It's the same ratio, right? Because are you using I times Z, or I should say I squared times Z, or are you using I squared times R, right? So you're either multiplying your I squared times a Z or times an R. So if you want the apparent power, you multiply it by your Z, and if you want the true power, you multiply it by your R. So really, we're interested in, we're interested in this. How do you turn the Z into an R? Well, here's your phase angle. Can you say SOHCAHTOA? Can you say x component of a vector is r cosine theta, right? Remember this stuff? We were playing with vectors. In other words, you take, and that's a little r, so that means this, the length of this vector here times the cosine of this angle here gives you the length of the r vector here. So that's why it works. So power factor equals cosine of theta, and I'm going to put in quotes, turns Z into R, and the effect is that the true power, you would take the apparent power, which is based on Z, you would multiply it by a power factor to base it on R instead. Okay, so I'm kind of throwing these words around here. I hope you're kind of picking up the gist of what I'm saying. The picture is it. The picture is it. The Z gets turned into an R by taking its x component, by taking it times the cosine of theta. So the power factor is the cosine of theta for that reason, and that's why this formula works. So again, I want to emphasize this because you go to Don's class and this is what he's going to be throwing at you. He's not going to throw the I squared R at you. He's going to throw that at you. Take the power factor cosine theta, and part of the reason he'll do that is because I'm talking about series, but there are other circuit configurations too. Like if you had some kind of parallel thing, it's not going to quite work to do just I squared R. So anyway. The good news is we have now encountered all the concepts that we need for this lecture. So why don't we just finish with example 2, which actually the best way to do this would be to have you try it. Pause the video, have you try it, and then come back and compare your answers to mine. Okay, here we go. Ready to compare answers? We've got a voltage applied to another one of these series RLCs, and they give us the the reactances in the resistor. Okay, they give us the ohms. Find the impedance of phase angle. Okay, so this is like before. You draw the resistor to the right. The resistor is 200 ohms, purely to the right. X component 200, Y component 0. XL is 50. Try to draw that up a bit. It's completely straight up. It has no X component. It's a pure positive Y component. And then the capacitor is down here, and it's only 30 ohms, but it's completely straight down. No X component. Down means negative 30 ohms. Okay, so the impedance then, if I compare 50 to negative 30, you can tell, well, it's going to be a little bit on the upside here. So the impedance is going to be up here someplace. It's going to line up. It's going to have the same X component as, you know, its X component is going to be the same as our. It's going to have an X component of, in fact, 0 plus 0 plus 200, right? That's what I was trying to say. And then the Y component would be, you got a 50, you got a negative 30. So that's 20 plus 0 is still 20. So there's your impedance vector. So the length of that impedance vector, which is a little r, not to be confused with big R, is do the square root of a 200 squared plus a 20 squared. And let's see what we got here. 200 squared plus 20 squared equals, take a square root of that, and we're getting about, I don't know how many sig figs I need right now. Well, my calculator's telling me this, 200.9975. Let's get real. Let's call this 201.0. That's good. 4 sig figs is a pretty healthy number. So I'm going to round the 0.99 is going to round up to a 1.0. That's ohms. And that's your impedance. Your impedance is 201 ohms, just almost exactly 201 ohms. The phase angle would be, do the shift tangent of the y over the x, 20 over the 200. And so the phase angle is 20 divided by 200 equals, well, it's, oh, I got to hit a shift tangent, don't I? Yep. And it comes out to just about, I'll use 2 decimal places on my degrees, 5.71 degrees is my phase angle. Positive, so voltage leads the current. Okay, current through the circuit. Well, you can always use the Ohm's law, except you don't want to use it that way because we have a series RLC circuit with AC electricity in it. So instead of the R, you use the Z. Okay, you can also refer to the table on page 1 if you like. But it's E times IZ. So we're trying to solve for the current, right? So that means I want the I by itself. So I should basically cancel the Z off of there. And so my formula, if I switch the 2 sides around, my formula is going to be this, E divided by Z. So I take my voltage, which they gave us, right? 120 volts RMS, divide it by the Z that we just solved for, 201.0. 120 divided by 201, boink, boink. I'm getting I is equal to 0.597015 amps, and we really should be good and hit our eng button and everything and call this 597.0 milliamps. A little more than half an amp, 0.6 amps, 600 milliamps. Cool. The apparent power. Well, you know what I'm going to do now is I'm going to, well, not much actually. I'm going to go, I'm going to use this formula. Again, that looks like Ohm's law, and it kind of is. The only difference really is we're using RMS, and remember the E results according to the I and the Z. So this is an apparent power, not a true power. So we take the E that they gave us, which was 120 volts, we multiply it by that, and I might as well put the 0.597015 in here, and we will get our apparent power. So times 120, 71 point, call it 64. it's apparent power, not watts, so you call it volt amps. 71.64 volt amps, which is what I got before. That's good. And then to find the true power, okay, this is where we're going to have some fun. Let's use our new formula. The true power is the apparent power times what's called the power factor, what is in effect the cosine of the phase angle. So take my 71.64 volt amps that I got for part C and multiply it by the cosine of the phase angle, which was what now? 5.71 degrees. 71.64 times cosine 5.71 degrees is, and I'm getting something like 71.29. And these are watts because it's true power dissipated. So in this case, not a heck of a big difference there, 71.6 versus 71.3, and that's because the phase angle was so small. So the smaller the phase angle, the closer the true and the apparent are going to be to each other. But if you have a big phase angle, your true power is going to be a lot less than your apparent power, because the cosine is going to be kind of a low number. So I guess we're at the end of our lecture there. Cool. And that ends our unit on the introduction to AC electricity. I hope you were grooving on all these volt amps and RMS values and phasors and all this cool stuff. Dig it.